Okay, folks, so let's start with asymmetric key encryption. Okay, please feel free to ask questions in case you have any. Yeah, just a minute. All right. So today we will study one of the very important protocol called Diffie Hellman protocol. Just a minute. Okay. Okay, so we are going to cover these topics: one-way functions, Diffie-Hellman key exchange, attack on Diffie-Hellman, and key exchange basics. All right. So, okay, before that, we'll look at very briefly about the concept of one-way function. We have already studied one-way function in when we studied hashing, right? Okay. Now, asymmetric key encryption uses one-way function very intelligently. Okay, so now we define one-way function as the function f which is on x, and so we have y which is output of the function, which is f is equal to y is equal to f of x. Now this given x, calculation of f of x which is equal to y is very simple, trivial, right? Okay, and the when we say simple, it means they're computationally very fast. It may take few nanosecond or milliseconds. Okay, but inverse of that, giving you y, getting from this x is computationally infeasible. It means that it should take, for normal computer, we say reasonable time to do this is 10,000 years. No, it's extremely difficult. Okay, impossible, like, in current, with the current technology. So these functions we use in asymmetric key cryptography. Crypto, right? And also we call it public key cryptography. Okay, and we are trying to solve some very important things out of this, right? The whole company is formed, there's a company called RSA, which of course got acquired, is based on this concept, right? And it's not very old, it came sometimes around 1975 or 80s. Now these are based on two mathematical problems, and the solution first is called integer factorization scheme. Okay, it's based on the fact that it's very difficult to factor large integers. Okay, and the algorithm based on this is RSA. Second one is discrete logarithmic scheme, and again it's computationally is a one-way function. Okay, and finding out log of some numbers which are in finite field is extremely complex. Okay, so a lot of other algorithms are based on this, are Diffie Hellman, LCML, and then we'll study digital signatures. Okay, just a minute. All right, so let's get back. So basically we'll look at only these two. Of course, there's another family called elliptical curve, which will not study. All right, now very important protocol is called Diffie-Hellman key exchange protocol. Okay, now note the word Diffie-Hellman, of course, is the name of the person. Okay, two people. I think two guys. I'm not too sure, or maybe one. I don't know. And then key exchange, right? Look at this word key exchange. What does it mean? We are trying to solve very important problem of key exchanges, right? Okay, so we'll come to that. Okay, so now symmetric key encryption is a very beautiful system, and most of the systems today in the world we use symmetric key encryption method. okay, because it is very fast and very effective. Okay, it's very fast. So what does it require? We have two entities, Alice and Bob. So we have and then we have as an input some message M, and then we have key, and we use encryption algorithm. And when this encrypted text, ciphertext C goes to Bob, he uses decryption algorithm using the same key. Now this key is same. The question that, and in today's world, earlier, and as I mentioned, I mean, these keys were transported manually, like a truck carrying keys of all employees of one company to another company, something like that. And very trustworthy resource, a person will distribute these keys within a sealed envelope and all that. Now, that's not the case today, because people are not sitting within the same city or whatever, right? So people are all across the world, and the two entities can be not only man but also can be a small machine, or it could be a car and garage and whatever, right? Okay, so now the problem is that we have to send the key over internet, which is insecure channel, is a leaky channel, right? Internet, there is it just provides you end-to-end pipe, and in between it does not guarantee that your message can reach to other end. See, or look at IP does not say anything whether your packet will reach to other end. It does not also say that your packet will reach properly. It does not also say that somebody in between will not watch your packet. Okay, so internet is insecure channel, and it is designed that way to give efficiency. All right, now the problem is that you need to send the key to other end, and in between you have people like Mallory. She can be very curious, and she is manipulative also. She can manipulate things out. Or Eve can just, curious one, and then you can see what's happening, while Mallory can do man in the middle attack. All right, so now how do we send keys then from one end to another end over internet? There's a question that scientists have trying to solve it, and they could get. Okay, so we'll study that. So there is a key distribution problem. How to distribute keys over insecure channel like internet. Second is that, if there are n people in an organization, and then each needs to exchange a pair of keys with each other. Okay, all right, if n is, so how many connections, how many pair of the keys will be exchanged? It will be of order n square. If n is the number of people, right? So it's equal to n into n minus 1 by 2. So order n square keys. And what is this number? N square is is a big number. If n, and for example, n is equal to, let's assume that, take company of size of TCS. How many employees TCS will have? Any guess? Approximately? Anybody?
Thousands.
Forget, yeah. Forget about thousand. It has got to be in few lakhs. You can just simply say revenue is 2 billion, 20 billion approximately US dollar. Each person, let's assume, earns maximum 100K average earning. Divide 20 billion by 100K. That's the average number of people. That's approximate number, not average, approximate number of people. So what will be 20 billion by 100K? How many lakhs? 1 billion is what? 1000 million? 100K is what? Okay, forget about the math. Do this math offline. It will be in few lakhs. Few lakhs is close to, let's assume 0.1, 0.5 million. Or let's assume even 0.5 million. Let's assume. Or let's assume even, 100,000. Okay, 100K. So 100K employees need to exchange key with 100K employees. How many order n square will be what? 100K into 100K is a very, very big number. How you are going to do that? Okay, so this is number of keys is a very, very problematic if everyone wants to communicate with everybody else in the organization. Okay, that's second problem. What is the third problem? Third problem is the problem of symmetric encryption. If Alice or Bob cheats, there is no way you can find out that Alice and Bob are lying. So there is no non-repudiation property. Okay, all right. So it means that if in this mechanism one cannot catch Alice or Bob if they lie. So we want to solve all these three problems with asymmetric key in cryptography. Okay, so these are problems we want to move to something and see that can we solve these problems, and then we'll see what are the issues, and then finally we'll see that can we combine these two schemes. Okay, all right. So the first important algorithm that came out in 1976 is called Diffie Hellman key exchange algorithm. It's a new direction in cryptography. Okay, it is first key exchange algorithm invented in one of the first formulation of public key cryptography. Subsequently, RSA and many others came. Okay, so goal of this algorithm is to create a very short life key, ephemeral keys, which is very, very short. It's a kind of session key. So Alice and Bob are creating a session. Okay, then they need to have same key, and the session will go only for very short time, and then these keys will be discarded. Okay, all right, and then these keys have to be discarded once session is over, and also we call them session keys. Okay, all right. So it means that now if with this method Alice and Bob must agree on some key k. Okay, now this k is going to be a random value, some random value, which Mallory in between cannot predict. All right, and this scheme Diffie Hellman is used in SSH, TLS, and IPsec. Okay, now let's look at this simple diagram. Can you see this diagram? Now this is not exact analogy, but it will give you some idea about it. You can see this diagram, right? Okay, let's take Alice and Bob agree on a common color, say yellow, and this is a publicly known. Okay, and in this one, Alice has a private color red, and Bob has a private color which is kind of blue, or maybe something else. Okay, and then Alice mixes this color and gets this color here. Okay, while Bob mixes to yellow the second color and get this color. Okay, now Alice sends this color to Bob over insecure channel. Now in between, Eve and Mallory can see that, but they cannot separate out this mixture, right? Because this mixture is of orange color, they cannot separate out. If, say for example, Mallory sees it, Mallory cannot separate out a red color and yellow color out of this. Yellow is, although yellow is a common knowledge, yet she cannot separate red out of it. Okay, all right. Similarly, Bob sends this light blue color here. Okay, now what happens that now once Alice receives this color, light blue, she adds to that her private color, which is red color, and she gets this color here, which is kind of yellowish gray kind, I don't know, some common. Okay, and similarly when Bob receives this color, which is orange, and mixes with it its own private color, then he will also get this. So these two are now common colors. In between, Mallory and Eve cannot separate out the colors. If she can separate out the color, like here, if orange color she can separate out the colors, then she can get this private key or private color, and then from that she can derive others, but that's not possibility. Are you trying to understand? Any question? It means that after mixing, whatever mixture you get of two things, it's very difficult to find out what has been mixed, because there are a number. It means that there will be infinite ways of separating that out. When Mallory sees this, and this may be one of the combination, right? But there can be a million other ways you can achieve this. There's essence, right? So now even looking at this, Mallory cannot separate out these two colors. But now if you use the same color, after receiving it from Bob, then you get the common color here. Okay, any question? Please think about it. Is the analogy which is close to something that we are going to study. Okay, now same thing is now in words. Suppose Alice and Bob wants a secret paint color. Eve can see the paint color sent between Alice and Bob. It means that Eve is sitting in between, like as we see here. Eve can see all the exchanges. Okay. Alice generates a secret color amber. Okay, here is shown different color. Here it is this one. Okay. Okay. Okay, and Bob generates secret color blue. Now amber and blue, A here represent amber and also for Alice. Blue, B represents it for blue and for Bob. So Bob generates color blue, Alice generates color A. A is secret to Alice and B is secret to Bob, that we know. And they want to they agree on a common color green, like the one which is available to everyone, like here. Okay. Okay. Now they mix their secret color with G. That's a common color, right? So now what Alice will get after mixing is AG, or green amber, or GA. Okay, and when this Bob mixes this color G with blue, he will get green blue. So this color, right? Okay, now Alice sends GA to Bob, Bob sends GB to Alice. Okay, Eve now knows, Eve is looking at the colors in between, she will see GA and GB. Now these colors are very hard to separate. She will try everything, but she cannot separate it out. Now Alice knows, now Alice has received GB from Bob, she will mix A, and then what will she get is GAB. Bob has received GA from Alice and he mixes color B, which is his private color, and gets GAB. And now we can see that both GABs are same. In between, What Eve knows? Eve knows is common color G, which both of them use, is a public color. Everyone knows that this is a common color, and she will also use GA and GB. Okay, from this, obviously, if she looks at GA and G, she cannot separate out amber out of it. Similarly, she cannot separate out blue out of this. Okay, she can only form, she will mix these two and she can get GA GB, which is not same as GAB. GAB is not same as GAGB. Okay, so this is the analogy. Any question? All right. Are you listening? Please concentrate again.
Sir, could you
Okay.
please explain the last point again?
This one. Okay, Eve cannot separate out colors, and idea is that she wants to generate GAB, which she cannot do because all she can is mix these two, and what she will get is GAGB, which is not same as GAB. So Alice and Bob are able to achieve color GAB, this color, which in between anybody looks at that, Eve or Bob cannot generate that. Okay, so we'll go back again. Just give me a minute. Okay. Look at this example. This is a common color with Alice and Bob, and everyone in the world knows about these common colors. But Alice chooses private color amber and Bob chooses private color blue, and they mix these two. Okay, and after mixing, Alice gets this color. Let's call it GA. This is, sorry, okay. Okay, all right. The colors are different here, so just forget for a minute. So these colors are common colors. This is a private color. This is a private color of Bob. Both mix this. Alice mixed this common color with private color. She gets this color. Bob gets this color. They exchange this color or public transport. And in between, Eve and Mallory see that and they cannot do anything about it. They can't separate the basic colors, these two colors that have been mixed. Although she knows that it's a yellow, is a common color. Okay, and after this, Alice mixes the private color and gets a color. This one is kind of mustard color, and then Bob also gets the common color after mixing his private color. Okay, all right. In between, what they can do, what Mallory can do is that she can take these two colors and try to mix it, then she will get something else. Same thing is shared here. Okay, so let's go ahead and then see. When we will required, we'll come back to this one. So color analogy says mixing two colors is easy, but separating the mixture of two colors is practically impossible. It's nothing but a one-way function. Okay, you take a cow milk, into this you add, you know, some other element. Let's assume that you mix into that whiskey. Okay, can you now, and you get something. Can you separate out milk out of whiskey? You cannot. Okay, so if you can define, is a kind of loose way of defining a one-way function. Okay, all right. So this definition we have seen. Now, see, what we are going to use here is modulo function. Modulo a prime. We'll look at only at prime numbers, and then we'll take a modulo function of that. These are one-way function. So now note that we are not going to get into mathematics. We don't have so much time. Okay, but it's very interesting proof. So for that you have to really understand modulo numbers. You would have done it in one of the courses, but at the same time there's a lot of theorems and proofs around it that is given in the book. Christoph Parr's book is just excellent. Okay, so just go through it if you're really interested in mathematics of this. Okay, all right. So we don't have time. Otherwise, we'll take 2 more lectures for this algorithm. So we don't want to do that. So because we'll have to cover some other topics as well. But I will give you references. Please go through it. Now the fx function, which is one-way function, we say, is we define this as g raised power x mod p. And you know the mods, right? How mods are calculated? Okay, so just for example, if we have 100 mod say 30, what will be answer of this? 10 is remainder, right? Okay, so we define fx is equal to g raised power x mod p, where p is very large prime. Now when we say large here means in the order of 2048 kind of size. Okay, the bit size, the number size is this much, and g is specially chosen generator. We'll look at what g can be, and g is obviously smaller than p. Okay, so p is very large prime, and g we choose, and p and g are public knowledge. Everyone knows that what p and g are. Okay, so now given x, which is a private thing, which is a private knowledge, which is not shared with public, is easy to calculate fx, because g raised power x mod p you can easily calculate. Okay, now is a one-way function, because given you this number g raised power mod p, which you have calculated after calculation, there is no known efficient algorithm to solve for x. It means that from this you cannot find out what x is in reasonable time. Reasonable could be 1000 years. Okay, all right. So sorry, let's go ahead. Okay, so now let's go into little bit more details. So Alice has a private key A, and she generates a private key, some number, some random number, some she decides based on pseudo random number she generates, right? And from that she derives a number A, which is equal to g raised power A mod p, given that g and p are known to everyone and p is large prime. Okay, similarly Bob has a private key B, which he generates using some random number algorithm, and generates a public key B, which is g raised power B mod p. So Alice generates this number, Bob generates this number, and they can publish it, they can share it with anybody. Okay, so now Bob sends the key B to Alice, and then Alice has his own private key A, this one. So she does this calculation, B raised whatever she has received from Bob, she raises power of that by A, so it becomes B raised power A, and then she does mod P. Okay, basically she just raises it to power A, and then of course because the whole calculation is based on modular mathematics, right? And you plus read about modular mathematics, you know, basically it gives you a series of numbers based on what is the value of P and so on. Okay, all right. So now what we get out of this? What is B? B is g raised power B, this one, right? So what we get out of from this mathematics, and there are of course some mathematical relationship that how you can get g, because B is g raised power B mod P, and then whole raised power A will turn out to be, because is a property, g raised power B raised power A mod p. Okay, this is a property. So now out of this we get this one, g raised power b raised power a mod p, which is nothing but g raised power ab mod p, because of some property which you can read. Okay. Similarly, Bob receives Alice key a, and then he raises it to power b. B is his own private key. A he has received from Alice, which is nothing but g raised power a mod p. Okay, and then raises power of that by b. So it, because of this kind of relationship, he gets g raised power ab mod p, which is nothing but this one, right? G raised power a power b here mod p, which is becomes g raised power ab mod p. Now we note that both Bob and Alice have the same key. Does it look like magic? In between, what will happen? In between, if Eve or Mallory tries to recreate it, what will they get? She will get g raised power a and g raised power b, of course in mod. So can she get from these g raised power ab by mathematical manipulation? Can she get? Yes or no? She also knows these numbers g and p. She knows g, p, g raised power a, g raised power b. Can she get out of this g raised power ab mod p? Yeah, of course, p is known, so mod anyway she can get. Can she get g raised power ab from these three, these four numbers? No, what she get is g raised power a plus b. Okay, please go through this relationship again, and then you'll see that in between Mallory cannot get g raised power ab, which is a common key. All right. So in practice, this algorithm is not used as it is, but we are also, once this common key is generated, then because key size will be very long, so we can apply a hash function to this and reduce the key size. So both parties, Alice and Bob, after generating the key, can apply a hash function and reduce the key size, and also it will bring some randomness into the game. All right. So if eavesdroppers cannot calculate the value of S. So now can we define it more formally? Everyone knows large prime P and generator G. P is generally of 2k size. Okay, and G is between 2 and P minus 2. All this theory is dependent based on some theory, right? Which you can read if you're interested. So now this is a discrete log problem because you cannot given, all these are one-way function. Given g raised power a mod p, you cannot find out a. Given this number, you cannot find out a. So Diffie Hellman problem is that says that you choose long random number a and b. Okay, and then of course you have to select g and p, which is a public knowledge. Okay, so everyone in the world will know g p, g raised power a mod p and g raised power mod p. Given that Mallory and Eve or anybody else cannot find in polynomial time difference between this g raised power a mod p and a random value r. It means that one cannot find out in polynomial time from all this knowledge this value of g raised power a b mod p. So this is the learning. Or cannot generate a random value r or some value r which is equivalent to this. All right. Okay. So this all this we have already discussed. So if Mallory in between gets g raised power a mod p and g raised power b mod p, she cannot generate g raised power ab mod p, but all she can generate is g raised power a plus b mod p, which is not the same as g raised power ab mod p. Okay, any question up to this point? Okay, again, this is not very simple theory, it's not easy, but please try to visualize it and read from the book. You can follow the book that's available in with Berkeley lectures. Go there and read the book, and also read other book like Christoph Parr's book is just excellent, right? So I have gone through 3-4 books before preparing these slides. Okay, all right. The same thing we can say here pictorially, that given random A, B and R, A is the key with Alice, B is key with Bob, and R is a random number. Okay, then common knowledge is this one. Mallory can see GP, G raised power A mod P, G raised power B mod P, and G raised power AB mod P. Okay. Oh, I'm sorry. This is not a public knowledge. This given this, okay, G raised, these three are public, these four are public knowledge. This is the key that they have generated. So this is one set of numbers. This is one set of number. Then we can say that this set of number is indistinguishable from the perspective of polynomial time attacker. So it's different from GP, G raised power A P, G raised power B, because these are known, and a random number which anybody in between can generate. Okay, so one person cannot generate the same R as this one in polynomial time. Same thing that we discussed earlier, just a different depiction of that. Okay, so so now more pictorially, let's see. This algorithm says that Alice generates a random secret key A, Bob generates a secret key B. Okay, she chooses, and these keys are usually very large in size, large, around 2K or something like that. But this is smaller than P. Okay, when we say it can be between 0 and 2 raised power 2048, 2 raised power 2, in between it can be any number. Okay, but size of number of bits to represent that number could be as large as 2K or even larger than that, depending on implementation. And P is a prime number which is larger than A. Okay, from this G is also a common knowledge, a public key, which is again smaller than P and based on some relationship. So from this, Alice calculates G raised power A mod P, Bob chooses private key B, and he calculates G raised power B mod P. Next thing is that they are going to exchange this. Public knowledge is G and P. So Eve at this point in time knows G and P. Okay, and then next thing is that this one is sent to Bob, like let's call it A, G raised power A mod P. This is sent to Bob. Bob receives G raised power A mod P. Bob sent this G raised power B mod P, which we call it B. Of course, here we have shown only G raised power P, which is nothing but G raised power B mod P. And Eve receives this. Okay, from this received number, Alice just raises his power by A, okay, and she gets G raised power AP mod P. And based on modular mathematics, we can see that by raising the whole power of B, which is G raised power B mod P raised power A, is translates to this one. Okay, similarly, Bob will raise its power by B. So what we'll get is G raised power A mod P. So both will get G raised power AB, of course mod P. In between, Eve or Mallory sees that using G raised power A mod P and G raised power mod G raised power B, she cannot create G raised power AB. Now both Alice and Bob will have the same key. Any question? Okay, all right. All right, all these points, please go through it. It's very simple, right? Let's look at example. We'll take two examples. And these are toy examples, right? These are not the real example because the key size have got to be very large. Okay, but it will give you the result, right? So Alice and Bob agrees in prime P. So we know that P and G are public knowledge and G is 5. So maybe their computer has all these numbers built in, algorithmically, or is known to everybody and they pull it out from somewhere. Okay. Now Alice and Bob have to choose some private number. So Alice chooses A is equal to 6, a private number, and she sends then G raised power A mod P, right, to Bob. So what is that? This is public key, a public number, because it's visible to all. So she does this. G is 5, so 5 raised power 6 mod 23, which comes to answer is 8. She sends 8 to Bob. You just do this calculation. 5 raised power 6, whatever number you get, divide it by 23, and it's an exact division. Okay, and whatever remainder you is 8, you send it to Bob. Alice sends it to Bob. Similarly, Bob chooses B is equal to 15 and then does G raised power B, which is 5 raised, G is 5, so 5 raised power 15 mod 23 gets 19. Now he sends this 19 to Alice. Okay, now Alice receives 19 and raises his power by his private key is A is equal to 6 and does mod calculation mod 23 and gets key as 2. Bob receives 8, this 8 which she has generated, raises power by its own private key, does mod of 23, gets 2. So 2 is the shared secret. Okay, another example is similar, right? It's nothing different. P is 23, G is equal to 2, Ls chooses A is equal to 5, computes A is equal to G, which is 2 raised power 5 mod 29 is equal to 3, sends 3 to Bob. Bob chooses B is equal to 12, computes B is equal to G raised power 12 mod 29 7. Bob sends 7 to Alice. Alice receives 7 and raises his power by 5 and does the mod calculation and gets 16. Answer is 16. Bob does the same thing and he receives what value Alice has sent, which is 3, raises by 12, does the mod calculation, gets the key as 16. All right, any question? Are you able to understand it? Yes or no?
Yes, sir.
Okay, all right. Let's move ahead. Now we have to see that what is the security. Okay, so for example, let's assume that P is a prime of about 300 digits and we are at least 100 digits. Okay, so discovering the shared secret given all these numbers will take larger than lifetime of the universe, even for this 300 digit value of prime P, and AB is approximately 100 digits. So it is extremely difficult to break and nobody could break this algorithm so far. Okay, now can we do attack on this one? Now so far we have talked about Mallory and Eve and they can just observe this, cannot do, and then can do some calculation by themselves, but they were not doing man in the middle attack. So actually I should have used word Eve rather than Mallory, right? Okay, So Eve just does eavesdropping. She can look at the number and can do manipulation, but she cannot do man in the middle attack. Okay, but Mallory can. Okay, so now let's say Mallory is in between. Okay, so Mallory comes here now. And this is what we have discussed so far, right? This is a normal Diffie Hellman key exchange that we have seen, just both receive the same key, right? Now let's see that can Mallory in between do this attack. Okay, now when we say man in the middle attack, it means that a message from Alice will not reach Bob. In between, it will be intercepted by Mallory, and Mallory has power to manipulate that. Okay, she can create another message, another number, send it to Bob. So it's just like this. G and P are public knowledge. Alice and Mallory is in between. She plays the man of the middle role. She generates Alice generates private key A, Bob generates private key B, and Mallory generates a private key M. Now all three calculate their public number, which they will send to each other. So Alice computes G raised power M mod P, Mallory computes G raised power M mod P, and Bob computes G raised power B mod P. And now Alice thinks that she is sending it to Bob, but actually is received by Mallory. Okay, so Mallory receives G raised power A mod P from Alice. Okay, and similarly she receives G raised power B mod P from Bob, but she sends her own public key, G raised power M mod P to both Alice and Bob. So Alice and Bob receives this public number which Mallory generates, but Alice and Bob do not know that it's coming from Mallory. Alice thinks it's coming from Bob. So based on this received number, she can create the key here, which is G raised power AM. Okay, and Bob similarly creates G raised power BM. Okay, now what can happen is that when Alice sends a message with this key, and Mallory has also created this key. Okay, because assume that interaction is happening between Alice and Mallory now. Similarly, Mallory, these are two separate communications now. Now, whatever message is being sent by Alice can be seen by Mallory because both have the same key, and similarly, Bob and Mallory have the same key. So she can do all kind of manipulations. Man in the middle attack. Any question? Okay, now we'll study in future something called digital signature to prevent from this kind of man in the middle attack. So the issues with Diffie Hellman is that this algorithm is not secure against man in the middle attack. Now Diffie Hellman is an active protocol. When we say active, it means that key generation is only for short period. The key lifetime is only for very short period, right? Okay, so it means that Alice and Bob needs to be online for same time for exchanging keys. What will happen if the duration of the exchange is very large or very long? If Bob wants to encrypt something and send it to Alice for her to use later, okay, then we have to find out what can be done. Okay, similarly, Diffie Hellman does not provide authentication. Okay, because we have seen man in the middle attack because Alice thinking she is communicating with Bob, but actually she is communicating with Mallory here because Mallory is doing man in the middle attack. All right, you got the point? So now, this is all about Diffie Hellman algorithm, and then we'll come with two other algorithm based on this. Okay, which is minor tweaking of this. We'll get one algorithm and then we'll study RSA algorithm. Okay, so key exchange basic in general, what happens is that every user generates two keys private key and public key and private key. Alice will generate public key and private key and public key, and then then if Alice wants to send something, okay, all right. So what we have seen is that it's a symmetric key setting right now, as we have seen earlier, okay, in Diffie Hellman. From using Bob's public key and Alice's own private key, common key is generated. Similarly, using Bob's public key, sorry, oh, Alice's public key and Bob's private key, again secret can be generated. This is what we have studied so far in symmetric key setting, but we have seen the man in the middle attack is possible. Okay, so in order to overcome that, what we do is that we tweak this slightly. Okay, all right. So, and then we come out with the next algorithm, which is that everyone generates 2 keys, and then we can use say for example, when Alice receives Bob's public key, she can use this to directly create a ciphertext. Earlier our emphasis was to create a common key here, right? So what we have done in this algorithm, okay, that we created a common key by using public key of Bob and private key, her own private key. Alice can generate a shared secret. Similarly, Bob can generate a shared secret. These people should have been exchanged here in this way anyway. All right, what we have achieved is common key, shared key, and from this, once both have the key available, then we use symmetric key encryption. But why can't we directly encrypt the message? Okay, so in this method, what we do is that once Bob's public key is received, Alice can use public key to encrypt the message she wants to send. There is a message here, so she will use Bob's public key to encrypt this message, send this ciphertext, and then Bob will use a private key to generate the plain text. So that's the method that we'll study in the next period, next class. Okay, all right. All right. Okay, any question on Diffie Hellman?